Okay, may I start recording the class? And let me share the screen. So yes, today is the last lecture from me for this semester. And the topics today is the manipulator Jacobian and the inverse of Jacobian metric. So today we're gonna begin with the review. The review of the Jacobian. How can we compose the Jacobian metric from manipulator? The general description on how can we compose the Jacobian metric. And as I mentioned in last week, that if we see example in one specific type of robot, we can get a clear picture on how can we compose the Jacobian metric from robot. So to the example, we will have the Revolute prismatic robot, 3 degree of freedom robot arm, and we're gonna try to compose the Jacobian metric that relate the joint velocity of the robot arm, the joint velocity, and the velocity at the end point. So yeah, after that, after we learn how to compose the Jacobian metric, we will check about how can we obtain the inverse Jacobian and have some description on how can we use the inverse Jacobian in the application. But by the meaning, I think we know that the Jacobian metric relate the endpoint velocity and the joint velocity. Here is what we know from last week. The Jacobian metric will relate the velocity at the endpoint and the omega vector at the endpoint to the joint speed. We may have n joint, and it's gonna relate to the velocity vector. Velocity vector consists of 2 parts: the linear velocity and the angular velocity. The linear velocity is 3/1 vector. The angular velocity also 3/1. So we're gonna have 6/1 vector for the velocity vector at the endpoint, and it's not depend on, it's independent to the number of the degree of freedom that we have. We may have n as 3 degree of freedom, or we may have n as 6 degree of freedom. But to describe the velocity at the endpoint, we have 3 components to describe the linear velocity with respect to the x, y, and z axis. And we have the omega, which is the angular velocity, 3 components also. And so yeah, this will be the same content with the previous week. We just review, and we will have example that describe the method to compose the Jacobian metric. But the new topics for today will be the inverse of Jacobian metric. But by the concept, the Jacobian relate the joint velocity to the endpoint velocity. Inverse of Jacobian. Inverse of Jacobian will relate the velocity at the endpoint to the joint speed. If we have our desired endpoint velocity, endpoint velocity, what should be the joint speed, the speed of the motor, of the prismatic, of the revolute that drive the joint? What should be the speed at the joint so that we can have the endpoint speed that we want? So to review how to compose the Jacobian metric, we begin with the infinitesimal motion at the endpoint. The depth of the endpoint position consists of the small displacement of the end effector and the small orientation change at the end effector. And yeah, the position vector by time, we will have the endpoint velocity and angular velocity at the endpoint. Here is the concept. And yeah, the vector form is this one. We have the Jacobian metric. That we need to find so that we can relate the endpoint speed and the joint speed. And the endpoint speed is 6 by 1 vector. And the Jacobian is written in the form the column, one column of the Jacobian metric. One column of Jacobian metric is composed from 3 by 1 vector of the Jacobian for the linear velocity and 3 by 1 vector for the angular velocity, which means in each column of the Jacobian metric, we have the dimension of 6 by 1. And it depends on how many joints that we have in the robot. The number of columns need to be matched with the number of degree of freedom, number of joints of the manipulator. So it means that the number of rows is fixed. The number of rows of Jacobian metric is fixed. The number of rows need to be 6. but the number of columns is depend on the number of joints that we have. And yeah, we gonna have the product of the metric of the Jacobian metric and the joint velocity metric. And we mentioned that we have the velocity, the linear velocity of the endpoint and the angular velocity of the endpoint. And the linear velocity is depend on only the Jacobian of linear velocity and multiply by the first joint velocity and until the linear Jacobian that relate the velocity to the joint end speed. For the angular velocity, we have the Jacobian of angular velocity, and it's gonna relate to the velocity of the first joint until joint end. And if we only consider the velocity vector at the endpoint, the velocity vector at the endpoint is 3×1 vector. It can be composed from the first Jacobian multiplied by the first joint velocity. And yeah, we know that the Jacobian that relate the linear speed to the joint velocity is 3×1 vector. And we're gonna have n Jacobian with n joint, and we said that for prismatic joint, JL1, any prismatic joint JLI multiply by the joint speed of joint I, JLI 3×1 multiplied by the joint speed of any joint need to equal to the velocity vector at the endpoint. So in the robot, if we consider joint I of the robot, if that joint is the prismatic joint, the z direction, the z-axis of joint I, will be zi-1 by the Dennewitz-Hartenberg notation, and the unit vector of the prismatic joint, is the unit vector that shows the direction of the zi-1 axis. And the joint variable of prismatic joint, is d dot. D is the distance in the prismatic joint, the offset that can be controlled by the actuator. D dot is the speed of the prismatic joint, and how this joint speed in the direction of zi minus 1 affect the velocity, the linear velocity at the endpoint. If we fix the rotation of the outer joint, if we fix the rotation of the outer joint and just consider only the effect of the movement in the prismatic create the linear velocity at the endpoint. Prismatic create linear velocity at the endpoint, and the direction of that velocity, is described by the unit vector. The unit vector also have the dimension of 3 by 1 unit vector. The unit vector have this direction, the same direction with the direction of the prismatic, and the same direction with the zi minus 1 of the axle that we attach, of the frame that we attach to the robot. And the magnitude of the velocity is equal to the speed of the prismatic, So we can say that if the joint is prismatic, the Jacobian vector of that joint is simply equal to b I minus 1 unit vector, bi minus 1 unit vector. But yeah, please note that the bi minus 1 unit vector have the dimension of 3 by 1. And yeah, the Jacobian for the linear velocity also has the dimension of 3 by 1. This is for prismatic. How about if the joint is revolute? If the joint is revolute, the linear velocity is if we need to write the linear velocity at the endpoint as a function of the Jacobian multiplied by the joint speed. If the joint is revolute joint, the axis zi minus 1 the axis zi minus 1 is the same direction with the rotational axis of the joint I. In the previous case, joint I is prismatic. Now, in this case, joint I is revolute. For prismatic, the direction of z-axis of joint I is point along the direction of the prismatic. If joint I is revolute joint, the direction of the z-axis will point along the rotational axis of the joint, and the joint angular velocity is described by the magnitude of rotational speed of joint I, theta dot of joint I, rotational speed of joint I, theta dot I, and the direction of the axle, vi minus 1, described by the unit vector, the unit vector This is the omega vector, The position vector that measure between the center of the frame I minus 1 to the endpoint, the relative position vector that point from the center of the coordinate I minus 1 to the end effector. Relative position vector that point from the origin of the frame I minus 1 to the end effector is this vector. If you want to find the speed, at the endpoint, velocity is equal to the omega vector cross product with the position vector. Omega vector has the magnitude of theta dot I and have the unit vector described by b I minus 1. Theta dot I magnitude b I minus 1 unit vector. This is omega. The relative position vector is this one. The cross product between omega and the relative position vector, if you use the right hand rule to obtain the cross product, you will get the direction of the velocity. At the endpoint. But for the numerical value, for the metric operation, we can form it like this. So it means that if you consider only, if you bring out the joint speed, it will multiply to the unit vector crossed by the unit vector. Wait a second. And yeah, sorry. We have the magnitude of the joint speed. We have the magnitude of the joint speed, and we have the unit vector that indicate the direction of the omega of the joint speed, and the cross product with the relative position vector. The relative position vector point from the origin of the frame I-1 to the end effector position. So if we see here, we can see that the joint speed is this one, the joint speed. And this vector, the cross product of the vector, should be the Jacobian vector for revolute joint. It means if the joint is revolute, the Jacobian for mapping the linear velocity of that joint I will equal to the unit vector indicate the z I-1 direction, the frame ci-1 direction crossed with the relative position vector of the origin of the frame I-1 to the end effector. And yes, this is for the mapping between the velocity Jacobian to the joint speed. How about the mapping of the omega angular velocity at the end point? Angular velocity at the end point. Angular velocity of the end point, similar way, if we come back to see here, the omega at the end point can be composed from this product of the metric. It means Jacobian of angular velocity of joint 1 multiplied by the first joint speed. And and we have n joint, so we have Jacobian for mapping the angular velocity. We have n vector from Jacobian angular velocity 1 to Jacobian angular velocity n, and multiply by the joint speed, if you see here, Q1 to Qn, Q is written in general form, but Q can be prismatic, Q can be revolute. In this case, also the same. We have the Jacobian metric that map the first joint speed to the angular velocity at the end point of joint 1 until joint n. So if the joint is prismatic, the J A I multiplied by Qi dot. If the joint is prismatic, do you think the joint will create any rotational speed at the end point or not? if the joint is prismatic. If we consider the joint I as prismatic, if joint I move with the speed of the I dot, endpoint will move with the same velocity vector. Endpoint will move with the same velocity vector. But the prismatic doesn't create any rotation, doesn't create any omega at the endpoint. So at the endpoint of prismatic, we can see only zero vector for the rotation. So although we have the prismatic velocity of joint I, but it's not create the rotation vector at the endpoint. It means that the Jacobian for angular velocity of joint I, if the joint is prismatic, it will equal to the zero vector with the dimension of 3/1. What if the joint is revolute? What if the joint is revolute? The Jacobian for angular speed of joint I multiplied by the joint speed Qi dot will equal to the rate of change in the direction at the endpoint, the rate of change in direction of the endpoint. So for the revolute joint, you need to imagine that if we have joint speed, and the unit vector that describes the direction of the omega at the endpoint here, the direction change at the endpoint will be the same as the direction change in any location. So the angular velocity vector at this axis will change the direction related to this axis in any point in the global space, the direction change, which is the effect of the velocity of this joint, will be the same. Which means that we can see the theta I dot with the unit vector b I minus 1 at any position, include the endpoint position. Sorry, I have better. Okay, and if we want to summary what should be the Jacobian of the angular velocity that relate to the revolute joint the joint speed or the magnitude of the omega and the Jacobian will equal to the unit vector, that describe the direction of the z I minus 1 of the joint I. The Jacobian for the angular velocity will equal to the unit vector of the frame I minus 1 of the z axis of the frame I minus 1. So we have this for the angular Jacobian for level and prismatic. We have this for the linear Jacobian for level and prismatic. So to summarize, for prismatic, any prismatic joint I, for any prismatic joint I, the linear Jacobian and the angular Jacobian for prismatic joint, the prismatic have the linear Jacobian as the unit vector that indicate the direction of z I minus 1. And for prismatic joint, for angular rotation, the Jacobian vector will be 0. So for linear motion, we have unit vector of the frame I minus 1. For prismatic, for linear motion, linear velocity at the endpoint, we have the direction of the unit vector I minus 1. Unit vector I minus 1 indicate the z axis I minus 1. And for angular rotation, prismatic doesn't change the rotational speed at the endpoint. So we have 0 vector. And for level joint, the linear Jacobian and the angular Jacobian. For level joint, the linear Jacobian is the most complicated one here. Is the cross product of the unit vector indicate the z axis of the level joint, indicate the z I minus 1 axis direction, and cross by the relative position vector, b I minus 1 unit vector crossed by the relative position vector that point from the origin of the frame I minus 1 to the endpoint position. Origin of the frame I minus 1 to the endpoint position. How about the angular Jacobian for revolute joint? The omega has the direction indicated by b I minus 1. The omega of the joint I indicate the direction by the unit vector b I minus 1, and it will affect the rotation at the endpoint with the same magnitude and direction of the unit vector at the endpoint. If we lock the outer joint and just rotate this joint, it will create the same rotational effect at the endpoint. So for the Jacobian, for angular rotation, the Jacobian of revolute joint will be the unit vector of the frame of the z-axis of the frame I-1. So until now, it seems like we know how can we compose by seeing the figure. By seeing the figure, we know what should be the unit vector. What should be the unit vector indicate the direction of the prismatic joint. What should be the unit vector that indicate the direction of the revolute joint? What should be the relative position vector? What should be the relative position vector? By consider the picture, we see the physical meaning of this quantity. But how can we obtain the numerical value of this thing? How can we obtain the numerical value of this thing? In order to obtain the unit vector, of the bi-1, bi-1 may be revolute, may be prismatic. But in order to obtain the bi-1, the idea is to use the rotational metric that relate the frame 1 to frame 0. The rotational metric is the function of the rotation by the joint angle 1 multiplied by the rotational metric of the second joint. Of course, if Q is theta, if Q is the prismatic, it affects the rotational metric. The rotational metric will depend on the magnitude of theta 1 or the prismatic displacement d1, depend on the form, the type of the joint, and depend on the magnitude. But finally, if we obtain the metric product from the frame 0 to frame I-1, from frame 0 to frame I-1, sorry, QI. No. I-1. Okay, if we obtain the metric products from frame 0 to frame I-1, if we obtain the product of the rotational metric, the rotational metric is 3 by 3 metric, right? 3 by 3 metric. How can we obtain the unit vector that is 3 by 1 vector? If we have the product of the metric from the frame 0 to frame I-1 as a function of joint 1, joint 2 until joint I-1, and it's gonna be 3 by 3 metric. But the unit vector should be 3 by 1. We need to multiply this thing by 3 by 1 vector. But what should be this 3 by 1 vector? What should be this 3 by 1 vector? We know that in any frame that attached to the joint, the z-axis the z-axis, the unit vector that indicates the z-axis. The unit vector that indicates the z-axis is 0, 0, 1. The unit vector points in the same direction, completely in the same direction with the z-axis. So the component for x-axis, for y-axis will be 0, have only 1 in the direction of the z-axis. So here is how can we obtain the numerical value of the unit vector indicate the z direction of the frame I-1. We have the product of the rotational metric from the first to the frame I-1, and then we multiply by 0, 0, 1 vector. How about, please note that this is the direction of z I-1. How about the relative position vector? How about the relative position vector? We introduce the metric x. We introduce the metric x I-1 until endpoint. The meaning of this x metric is the metric that relates the origin of the frame of n effector to origin of the frame I-1. The idea is we obtain the homogeneous transform metric. Homogeneous transform metric of first with respect to 0, and it's gonna be the function of joint variable Q1. The second homogeneous transform metric relates frame 2 to frame 1 and will be the function of the joint variable. We obtain the product of the metric until the last joint. Last joint means if we have n joint, we have homogeneous transform n with respect to n-1 and as the function of the joint n. And then we multiply by x vector. X vector. X vector means 0, 0, 0, 1. X vector means we know that T the homogeneous transform is 4x4 metric. We have 9 components for the rotational metric. We have 0, 0, and we have 1, and we have these 3 components. We have these 3 components for the position. So this will be 4x4. X metric, X vector will be 4x1. And the component here will be 0, 0, 0, except the last one will be 1. The 0, 0, 0, the meaning is X vector indicate the origin of the frame n, origin of the frame n effector, origin of the n effector frame. Now we have origin of the n effector frame, but the x that relate the relative position between n effector and the frame I-1, the frame I-1. We still need to compose the origin of the frame I-1. Now, this part we compose the origin of the n effector frame. The idea how to obtain the origin of the frame I-1, we use the same concept. We count from the joint 1, joint 2, joint 1, joint 2, until joint I-1, joint I-1. And multiply by x bar again. X bar 0, 0, 0, 1 again. So yes, this is the idea. And finally, if we have the product of 4 by 4 metric and multiply by 4 by 1 vector, we have 4 by 1, and we subtract by here. This one indicate the origin of the frame I-1, origin of the frame I-1. So the relative position vector of n effector and of the frame I-1, we subtract n effector by origin of the frame I-1. And of course, what we are going to have here is 4 by 1 vector. Is 4 by 1 vector. And we're gonna have 3 components, and the last component will be 1. The last component will be 1. We are going to find this one. The relative position vector. The relative position vector is this 3 component. In the x bar. No, we not call it x bar anymore. X bar only be 0, 0, 0, 1. But this one, the value can be anything inside here. But the first 3 component will be the relative position vector between the origin of frame I-1 and n effector frame. Here, this first 2 slides will be the review from what we learned in the previous week, and in the real application, how can we compose the Jacobian metric for real manipulator? This is the example of manipulator. This manipulator have the global, the base frame x0, y0, and z0. And the first joint is level root joint, and create the rotation by the joint variable zeta 1. And the second joint will be this level root joint. This level root joint also create zeta 2 deviate from the vertical direction. If zeta 2 is 0, it will point the thing upward. So if we rotate zeta 1, we rotate about the vertical axis, d0. If we rotate zeta 2, we are rotating about the axis d1. The unit vector we mentioned before, the unit vector that indicate the z direction of the frame is unit vector b. So for z0, we have b0 unit vector. For z1, we have b1 unit vector. The last joint is the prismatic joint. The prismatic joint. The prismatic joint can control the offset d3, and the direction of the prismatic, will be the direction of z-axis 2, and the unit vector that indicate the direction of z2 will be unit vector b2. So let's check the joint displacement. The joint displacement vector. How many joint displacement vector in here if we need to form? We have joint variable theta 1. We have joint variable theta 2. And we have the joint offset that we can drive the prismatic as d3. What should be the unit vector? The unit vector that indicate the z-axis. The unit vector that indicate the z-axis. b0. If you see b0 here, no matter the angle change, no matter what is the angle theta 1, the unit vector that indicate the z0 axis never change with theta. b0 unit vector always be 0, 0, 1 with respect to the global coordinate. b0 is the z-axis of the frame 0. Always be 0, 0, 1. What is the direction of unit vector b1? Where is b1? b1 point along the z1 direction. b1 unit vector point along the direction of z1. The direction of z1 is the axis of rotation. The axis of rotation of the revolute joint. If the theta 1 is 0, this joint will point along the let's see here. It should correct. Yeah. If the theta 1 is not rotated, if theta 1 is not rotated, the z1 will be in the same direction with y0. But now the theta 1 is rotated. By theta 1. So maybe we can draw this. like here, and the theta one in the beginning, the z1 point in the same direction with y0, but if we rotate by theta 1, it means that the z1 make an angle theta 1 here with the angle with the axis y0. If we look from the top view, we have x0, we have y0, and in the origin, C1 point to this direction, but after that, we rotate by theta 1. We rotate by theta 1. So this is the direction of C1 direction. Okay. So the unit vector that indicate the direction of Z1. Now we can see that this one will be C1 psi theta 1. This one will be C1. No, sorry. The unit vector has the radius, the magnitude of 1. The unit vector has the magnitude of 1, and the direction changed by the theta 1, and the component here with the magnitude of 1, this one will be psi theta 1, and this one will be cosine theta 1. So the direction of C1, the unit vector that indicates the direction of C1, in the x-axis, it should be plus x and minus x, right? So it should be minus psi theta 1 in the x direction. If you see again in the picture, here is the direction of C1. It makes an angle theta 1 with this. It makes an angle theta 1 with this. And here is the direction of C1. So if we consider the component along the x-axis, it should be minus psi theta 1. And if we consider the component in y-axis, it should be cosine theta 1. And if we consider the component of C1 along the c-axis, it's gonna be 0 because it's always orthogonal to the z-axis. How about the unit vector B2? The unit vector B2, if we see the projection of B2, on the horizontal plane, we will get this one and this one. This line this line, the length will be B2 sine theta 2. This length will be magnitude of B2 and sine theta 2. But magnitude of B2 is 1, right? So yeah, by the way, if we projection from the top view, B2 will lie on the same line with this on the horizontal plane, x0, y0. And the length of this component, the projection will be sine theta 2. If we project to the x and to the y with the theta 1, what we have in the x-axis here will be sine theta 2 cosine theta 1. Sine theta 2 first and cosine theta 1. This one is sine theta 2. This one is sine theta 2 and projection to the x with cosine theta 1. If we project to y, it's gonna be sine theta 2 and sine theta 1. And the projection of B2 in z-axis will be cosine theta 2, cosine theta 2. So this is the unit vector indicate the direction of the z-axis of the frame 0, frame 1, and frame 2. I compose this by looking at the picture, by looking at the picture. But if you don't like this, if you want to go to the direct method, if you want to compose the unit vector, you need to compose it from the rotation metric and multiply by 0, 0, 1. The rotation metric, it means if you want to have this, you may need to obtain the rotation metric of 1 per 0. B0 is the rotation metric of 1 per 0. B1. Wait a second. Bi minus 1 until 0. Wait. 0. B0. No, B1 is 1 per 0. B1 is 1 per 0 of joint 1. 1 per 0 of joint 1. Okay, B0 don't need to obtain from here. For here, we need to begin from B1. B1 is equal to the rotation metric of 1 per 0. B1 composed from rotation metric of 1 per 0 with the rotation of theta 1, and then multiply by 0, 0, 1 that indicate the z-axis. So the rotation metric of 1 per 0, how can we obtain the rotation metric of 1 per 0? It means we have the unit vector of x-axis of the new axis x1 dot x0, x1 dot y0, and x1 dot z0. We have y1 dot x0 y1 dot y0 and y1 dot c0, and we have the new z-axis dot x0 c1 dot y0 and c1 dot c0, and multiply by 0, 0, 1. So yeah, we consider x1 and x0. Here again, we have where should be the direction? Where should be the direction of the x1? Where should be the direction of the x1? In this picture, you can see the C1, right? We have C0, we have C1, and we know that X and Y maybe in this case, the theta 1 should indicate how the x1 deviate from the x0, x, y, c, x, y, c. Okay, so theta 1 indicate how the x1 deviate from x0. This should be the direction of x1. And to compose this rotation metric, x1 and x0, this is x1, this is c1. x1 and x0 with the dot product, we have cos theta 1. x1 and y0, x1 and y0, we have sine theta 1. x1 orthogonal with the 0, we have 0, and y1 is in this direction. y1 with x0 will be 0, y1 with y0 also 0, and y1 with c0 is in opposite direction, cos 180 degree will be -1, and c1 make with x0 will be minus sine. c1 make with y0 will be cosine theta 1, and c1 is orthogonal with c0, so we have 0 for the last component and 0, 0, 1. So by here we can see that the unit vector b1, is equal to minus s1 c1 and 0. You can compose the unit vector by this way. If the system is complicated and you cannot see by eye, cannot figure out by eye, you can obtain it by the rotation metric. If you want to obtain B2, you need to find the rotation metric 1 per 0, theta 1, 2 per 1, theta 2, and then multiply by 0, 0, 1. And then you will get this one. I think you can check. And yeah, now we compose the rotation metric. How about the relative relative position vector. How about the relative position vector? The relative position vector may be in this case, we may have relative position vector of frame 1 to n factor and relative position vector of in this case we have frame 1, frame 0. We have frame 1, frame 0, and frame 2. Maybe we may need maybe 3. Let's see this equation first. If we need to obtain the relative position vector of from frame 1 to n factor, it needs to be from frame 0 to n factor overall and subtract by the relative position vector from frame 0 to frame 1. Does that make sense? Here is the overall relative position vector from origin of the frame 0 to the n factor point, and this one will be the relative position vector of frame 0, origin of frame 0 to origin of frame 1. And the difference between this will be the difference between the relative position vector between the origin of the n factor frame and the origin of the frame 1. So from 0 to n factor, from 0 to n factor, the relative position vector from 0 to n factor. How can we obtain the relative position vector from 0 to n factor? We may need to begin with the X metric from 0 to n factor, the X metric from 0 to n factor, which is equal to the homogeneous transform 1/0 of zeta 1, 2/1 of zeta 2, and 3/2 of the offset D3, and then multiply by the X bar vector, and then we can pick the relative position vector. But I don't want to compose the homogeneous transform. You can check and compose the 4x4 metric and multiply. But for me, I know the physical meaning. of this. The physical meaning of the relative position vector measure from origin of the 0 frame to the n factor frame is the position of the n factor point, D3 is the offset. This one. The length of the projection here, is D3 psi theta 2. D3 sine theta 2, which means this one is D3 sine theta 2. If we have the cosine theta 1 component, we will have this one. So this one will be D3 sine theta 2 cosine theta 1 will be the position of the endpoint in x direction, will be D3 sine theta 2 cosine theta 1. And the projection in the y component here will be D3 sine theta 2 and and sine theta 1, sine theta 1. And the position in c direction, will be L0 plus by D3 cosine L0 plus D3 cosine theta 2 cosine theta 2. So the relative position vector from the origin of the braid frame to the origin of the end effector frame will be, for the x-axis, D3 D3 sine theta 2 cosine theta 1. In the y-axis will be D3 sine theta 2 sine theta 1. And in the z-axis will be L0 plus D3 cosine theta 2. The z-axis is independent to the theta 1. Is independent to the theta 1. But here is 4 by 4. X is 4 by 1. This one is equal to 0, 0, 0, 1. So this one still need to be 4 by 1 to make it correct. But just the vector, the relative position vector, it's just this first three components. It will be the relative position vector from frame 0 to the end effector frame. If you have time, you may try to derive the homogeneous transform metric and obtain the product of the metric, and then multiply by this vector and see if we have the same result for the relative position vector. How about this one? How about this one? How about this one? The relative position vector that relate frame 0 and frame 1. The relative position vector that relate frame 0 and frame 1. If you want to write this one, we need to have the homogeneous transform of 1 per 0 and theta 1 and multiply by x bar vector. But you can see by eye, the position of the frame 1, origin of the frame 1. Origin of the frame 1, O1 is here. O1 is in the coordinate. O1 is in the coordinate 0x, 0y, and L0 in the Z. compared to 0, 0, 0 position. So yeah, the relative position vector for here is just 0, 0, and L0 in the Z direction. But using the X metric, please don't forget to put 1 as the last component. But for the relative position vector, it's the first 3 components is what we want. We compose this one so that we want to find this one. The relative position vector that point from the origin of the frame 1 to the end effector. And the relative position vector from frame 1 to the end effector should be composed from the position vector that point from frame 0 to end effector, subtract by the one that we have from frame 0 to frame 1. So what we have 0 to end effector. 0 to end effector will be D3 S2C1 and D3 and S2 S1 and D3 C2 and subtract by 0, 0, L0. This one also have L0. Okay, so finally, the relative position vector from 1 to n effector is equal to D3 sine theta 2 cos theta 1, D3 sine theta 2 sine theta 1, and D3 cos theta 2. And yeah, why I need to compose this thing? We want to construct the Jacobian metric. We want to construct the Jacobian metric that have the component of Jacobian linear velocity mapping to the joint 1 angle, Jacobian that relate the angular speed to the joint 1 speed, Jacobian that mapping the linear velocity of joint relate to the joint 2, and angular speed relate to joint 2 speed, linear of joint 3, angular speed at the end point that relate to the joint 3 speed. We want to have this. But from the summary, we know that we have prismatic and we have level loop. The first two joints are level loop, and the last joint is prismatic. So for level loop, JL should be this one, JA should be this one. For the level loop, we have unit vector 0 crossed by relative position vector from 0 to n effector. And we have B0. Does that make sense? Come back to here. I just composed JL1. JL1 should be B0 crossed by R0E and B0. B0 crossed by R0E and B0. JL2 should be B1 crossed by R1E and B1 for the level root. For the prismatic joint, it's just BI minus 1 and 0 vector. BI minus 1 is B2 and 0 vector. So what is this one? What is this one? The B cos B0 cos R0E. B0 cross R0E. Okay, B0 cross R0E. B0 is 0, 0, 1. No. The cross product, it should be better to have IJK. And B0 is 0, 0, 1. R0E will be this one. R0E will be this one. D3 S2C1, D3 S2S1, and L0 plus D3C2. So we have D3 and S2C1, and we have D3 S2S1, and we have L0 plus D3 C2. We need to obtain the cross product of these two vectors. The method that I suggest here is we extend these two columns. We extend these two columns. And when we obtain the product of this, it will be positive. And for the upward, it will be negative. So I multiplied by 0, we get 0, J, 1, and D3. J, 1, and D3. So we have D3, S2, C1, J, positive. And for the upward, we have 0, and we have this one. But it should be negative because it's upward product. So we have D3, S2, S1, I. So if we write this in the vector form, it's equal to minus D3, S2, S1, D3, S2, C1, and 0, K. We have this one. How about this one? This one. The unit vector B1 crossed by the relative position vector from origin of frame 1 to the end effector. IJK B1 minus sine theta 1 cos theta 1 0. And relative position vector from 1 to n effector. Relative position vector from 1 to n effector is this one. Relative position vector from 1 to n effector D3 S2 C1 D3 S2 S1 and D3 C2. Again, we extend the two columns. We have minus S1 D3 S2 C1. We have C1 and we have D3 S2 S1. And the cross product, we begin with this one. We have D3 C1 C2 I. This one has 0. This one has minus D3 S2 S1 square K. For the upward, we have this one. D3 upward is negative, right? D3 S2 C1 square K. This one we have 0. This one minus will be positive. D3 and C S1 C2 S1 D3 S1 C2 J. So for the I component, we have D3 C1 C2 D3 C1 C2. For the J component, we have D3 S1 C2. And for the K component, sine square plus cos square equal to 1, right? We can sum these two common terms. So it's gonna be minus D3 S2. Just like this. This will be 1. Okay. So yeah, we have everything now. We can obtain B0, B1, B2 from the previous page, B0, B1, B2. And for the cross product of unit vector and relative position vector, we also done here. So Jacobian of this robot is this one first, minus D3 S2 S1 D3 S2 C1 and 0. How about B0? B0 is 0, 0, 1. B0 is 0, 0, 1. And B1 cross the relative position vector will be D3 C1 C2 D3 S1 C2 minus D3 S2, and B1 will be minus sine 1 cos 1, minus sine 1 cos 1 and 0. And B2 B2 will be, wow, sine 2 cos 1, sine 2 sine 1, sine 2 cos 1, sine 2 cos 1, sine 2 sine 1, and cos 2, right? Yeah, cos 2, and 0 vector, and we have 6 row and 3 column because we have 3 joint. So this is the Jacobian of this robot. Is Jacobian of this robot. Okay. The last topic for today. For here, maybe, yeah, as I mentioned, today is the last lecture. Tomorrow, maybe we're gonna talk about the project, but today is the last lecture. So the last topic for our class is the inverse of the Jacobian metric. For the forward kinematic, inverse kinematic, you know what is the, what is the purpose of obtaining the inverse kinematic? Obtaining the inverse kinematic, you need to, you want to find an answer. If you want the n effector to go to some position, what should be the joint angle so that the n effector can move to that position? The inverse of Jacobian application is in the same way. Before this, we obtain the Jacobian metric to relate the joint velocity to the endpoint velocity and angular velocity. The inverse of Jacobian, we are going to relate the desired endpoint speed, endpoint angular speed to the individual joint speed. As I mentioned before, that the position speed and angular speed is related to the joint speed by Jacobian. If we have the inverse of the Jacobian multiplied by the velocity vector at the endpoint, we're gonna have the joint speed that we need to control so that we can have the position that we want. But one concern is that we need to make sure that the Jacobian, the inverse of the Jacobian, is solvable. I mean, we need to know if the Jacobian metric is full length, and if we can find the inverse, and if we cannot find the inverse in some configuration, the robot may become singular. At that point, robot becomes singular. So in this topic, we will show example when the robot become have the singular configuration, Yeah. So we begin with the simple planar robot arm, 2-arm robot, and yeah, make it simple. The length of the arm equal to 1, and we if you want to obtain the x and y, we know that x equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Y is L1 sine theta 1 plus L2 sine theta 1 plus theta 2, right? Before this, we obtain the Jacobian metric. We obtain the Jacobian metric by we relate x dot and y dot, the speed x dot and y dot, to the joint speed theta 1 dot and theta 2 dot, right? Yeah, make it easy by let L1 and L2 equal to 1. The length is equal to 1. So the Jacobian for here have 4 components. The first component, you need to have the curve of the x position by theta 1. The curve of x position by theta 1. So dip cost will be minus psi. Dip cost will be minus psi. And dip cost of theta 1 plus theta 2 by theta 1 will be minus psi of theta 1 plus theta 2. Here is the first component. The second component, we dip by theta 2. We consider theta 1 as constant. So we have minus psi theta 1 plus theta 2. Just only this, theta 1 plus theta 2. And for this component, we dip y by theta 1. We dip y by theta 1. We have cos theta 1 and cos theta 1 plus theta 2. And we did this one by theta 2. We have cos theta 2. No, cos theta 1, 2. Cos theta 1 plus theta 2. So this is the Jacobian. If this is the Jacobian, what should be the inverse? What should be the inverse of Jacobian? If you have metric A, B, C, D, the inverse of the metric is 1 per that. That means AD minus BC, right? And the adjoint of the metric 4 by 4. You need to reveal what is the adjoint of the metric. But yeah, by this component. So if this one is Jacobian, what should be the inverse of the Jacobian? Why not we try to obtain the determinant of this one first? The determinant will be the determinant of minus S1 minus S12 minus S12 C1 C12 and C12. The determinant of this one gonna be minus S1 C1 minus C1 S12 and plus C1 S12 and plus S12 C12, right? S minus S1 C1 minus C1 S12 and minus will be plus C1 S12 plus C12 S12. That's it. So wait, I do something wrong. C1 is this one is C12. I'm sorry, C12. So this should be S1 C12. Oops. S1 C12 and yeah, S12 C12, S1 C12, S12 C12. Okay, so yeah, here are the same. And finally, we have psi theta 1 plus theta 2 cosine theta 1 for this one, and subtract by cosine theta 1 plus theta 2 and psi theta 1, which is equal to psi of theta 1 plus theta 2 and subtract by theta 1, and is equal to psi of theta 2. So the determinant here is psi theta 2, and the adjoint is this one. So the inverse Jacobian for this case is 1 per psi theta 2, and the metric will be C12 and minus S1 minus S12 and S12 minus C1 minus C12. So yes, we have the inverse Jacobian here. We have the inverse Jacobian here. The objective of obtaining the inverse Jacobian is we want to relate the joint velocity. We want to relate the joint velocity theta 1 dot theta 2 dot. The joint velocity is equal to the inverse Jacobian multiplied by the velocity vector. The inverse Jacobian 1 per psi theta 2. Inverse Jacobian C12 S12 and minus C1 C12 minus S1 minus S12. This is the inverse Jacobian. Inverse Jacobian multiplied by the endpoint velocity. Vx and Vy is the linear velocity at the endpoint. So now we are going to relate the joint velocity and the endpoint velocity. So theta 1 dot is Vx cosine theta 1 plus theta 2 and Vy sine theta 1 plus theta 2 and dy by sine theta 2 divided by sine theta 2. You can see that now, if we want to have the Vx and Vy at the endpoint, and in this condition, theta 1 and theta 2 is at this position, we need to drive the speed for the joint one so that it corresponds to the requirement for theta 2 dot. The same way, Vx need to multiply to this one. So minus Vx cosine theta 1 minus Vx cosine theta 1 plus theta 2 and minus Vy sine theta 1 and minus Vy sine theta 1 plus theta 2 and dy by sine theta 2. V2 and V1 of the joint speed need to be in this condition so that we can obtain the Vx, Vy that we decide at the endpoint. But what is the important thing I want you to see in these two solutions? I want you to focus on sine theta 2. The determinant of the Jacobian metric, the sine theta 2. The robot will have the singularity point when the sine theta 2 equal to 0, which means theta 2 will be 0 degree or 180 degrees. What's gonna happen to this robot if theta 2 is 0 degree or theta 2 is 180 degree? If theta 2 is 0, the robot will lie in this, how to say, the trajectory can be along the circle like this. It means we cannot, if the theta 2 is 0, we cannot create the velocity in the radial direction. We can only generate the velocity along the tangential direction. Also, when the theta 2 is 0, it means the arm will bend like this. We cannot create the velocity along the radial direction if the theta 2 is 0. we can only rotate the theta 1 about the origin, and the velocity can run along this line only, but we cannot create the radial velocity. So we have two possible singular points when the theta 2 is equal to 0 and 180. When theta 2 is 0 or 180, maybe the Jacobian may change. The Jacobian relate Vx, Vy to the joint speed, right? If the theta 2 becomes 0, if theta 2 becomes 0, this will be minus sine theta 1 and minus sine theta 1. It's gonna be minus 2 sine theta 1. If joint 2, theta 2 becomes 0, this will be minus S1. And this is gonna be cos theta 1 plus cos theta 1. And this is gonna be cos theta 1. Or if theta 2 equal to 0 or 180 degrees, Jacobian will change to this one. And Jacobian will change to this one. This means maybe you can split it to be, you can see that it have the same component here. These two, the Jacobian JL1 and JL2. Now, the Jacobian that respond to the joint 1 and joint 2 now are parallel. And yeah, the endpoint can only move perpendicular to the link. Endpoint can only move perpendicular to the link, and the Jacobian are parallel. It means parallel means you don't need to separate. You don't need to separate the Jacobian. You don't need to separate the Jacobian. You don't need to separate the Jacobian to be two terms like this. You can combine it to be, and the joint speed, you can combine it to be like this. And yeah, you have two joint, but you need only one Jacobian. The two Jacobian are not linearly dependent, they are parallel. And you don't have your freedom to drive the velocity independently. You can only have the velocity in the perpendicular direction to the joint direction when the theta 2 is 0 or 180 degrees. So yes, that's all for today. We see what is inverse Jacobian. What is the application of inverse Jacobian? We see one simple example how to derive the inverse Jacobian for 2x2 Jacobian metric. And we have a short introduction about the meaning of the singularity point when the depth of the Jacobian becomes 0. And we also see a good example to obtain the Jacobian metric for 3 degrees of freedom RRP robot. And we also have review for the concept of the Jacobian. How can we compose the Jacobian metric? So yeah, that's all for today. And to talk about the project and the exam, good news is we can extend the submission deadline for the robot project. Maybe I will check your progress on next week presentation first, what you have done, and I will discuss with Ajahn Pongsan about our final exam and the score for the project. We will try to increase the score for the project, and we will check deeply in detail what you have done for the project. How did you apply the knowledge after the midterm? How to obtain the inverse kinematic of the robot? And we will try to minimize the written exam, the score in the written exam for the final. Maybe just a few concepts that we still need to check. We're gonna have the final exam, but I will try to allocate the score from the final exam to the project and extend the time so that we can enjoy the project. So I will stop record the class from now, and after I receive the record, I will share it to you. So thank you.